Hello folks, this is my second lecture of the acids, bases, and buffers unit. I still don't know how many, but this is the back of the first page of notes and this last square here. And here is assistant and the baby. Hello baby.
I am the assistant.
The assistant
The
baby.
babysitter.
And we'll see how long he lasts. He's getting sleepy. Alright, so here we go. We got through the end of this box with the titration graph, and now we're going to talk a little bit about indicators and what they are and how they work, and then we're going to do a long problem.
Oh boy.
I know.
We like
Long problems are my favorite kind of problem. Okay.
A lot of paper.
This is not paper, this is the computer.
I'm just telling your students.
Oh.
You're going to want a lot of paper.
Sure. Alright, indicators. Indicators are the colored things that you drip into your solution of some kind to find out what pH it is. And they tend to be one color in a more acidic situation and a different color in a more basic situation. They will switch colors at some given pH, and different indicators switch colors at different pHs. So you might have an indicator that switches colors at pH 5. So when it's below pH 5, it's yellow, and when it's above, it's blue. You might have an indicator that switches colors at pH 8, and below pH 8, it's yellow, and above, it's red. And you might have one that switches at pH 7, and below it, it's colorless, which most people call clear, but that's not the same thing as colorless. And turn pink at when it is more basic. So you switch from one color to another at a particular pH, and when that switch happens in lab, you know that you've hit that pH.
Litmus paper?
Litmus paper is paper that has got that indicator all in the paper. Typically an indicator is a drip that you would drip into the solution, and sometimes they will put it on a slip of paper, and then you put that in the solution and it changes the color of the paper. Litmus paper is blue or red. Red is the color when it is in something more acidic than pH 7, and blue is the color when it's something more basic than pH 7, and when it's got pH 7 it's actually sort of vaguely purple. So that's an indicator. That is a good example. Thank you, assistant. So indicators in general are weak acids. They're really large, complicated, organic weak acids. And I haven't mentioned this, but any acid that is an organic acid, you'll be able to see that it's an organic acid because it's got a bunch of carbons and all that stuff in it. Tends to have, carbon. Pen.
Come out of hiding.
Yeah, there we go. It'll have carbon, and then it'll have it'll be attached to one carbon that has an O and an H and a double bond O. This is part of the organic chemistry unit. This is an ending that is called a carboxylic acid. And what you can see is that this H is attached to an oxygen that drags a lot of the electrons that way, and another oxygen that's dragging the electrons that way as well. So these two oxygens serve to cause this hydrogen to have feelings of wanting to leave. So if you have this ending on the end of something organic, and it doesn't really matter what's over here, then you have some kind of weak acid. So it's a carboxylic acid of some kind. All right. Indicators are some carbony thing, indicatory, with an H on the end that can fall off. And here it is falling off with an H plus and leaving the rest of the molecule behind. Indicator, in this IN does not mean the element indium in this case. It means the indicator molecule. The big molecule, we don't really feel like writing it. This is how you represent that reaction. And what's happening is, if you're in an acidic solution, you have a lot of H pluses. And if you remember Le Chatelier's principle, if you have a lot of H pluses, that's a lot of this side, it's going to shift left as a reaction to that, to kind of undo that. So when it is acidic, it shifts away from the H pluses. When it's basic, it does the opposite, and so it will shift to the right to dissociate more H's to kind of counteract the fact that it's basic. So it shifts left in acidic solution to the joined hin, and it shifts right in a basic solution to a separated h and in. And the hin molecule is one color. The in minus molecule is a different color. And so you kind of have different levels of these, and right in the middle is where you would end up with, if you've got like yellow to blue, right when it's balanced, it's sort of green because you have some yellow molecules and some blue molecules. Okay. So there you are. A couple examples of really frequently used indicator molecules are phenolphthalein. You've got to say the f and the th if you're going to say it properly. That's phenolphthalein. At pH 8, it changes from colorless in acid to pink in base. So colorless from pH 0 all the way up to 7.9 or whatever. At pH 8, it switches to pink, and it's pink from pH 8 all the way up basic. Skipping this one, we'll come back to it in a second. Methyl. You've got methyl red, you've got methyl orange. There are a couple of methyls. And it's red when it's more acidic than pH 5, and it's yellow when it is more basic than pH 5. And one thing that you need to do is you need to pick an indicator that's, when you're doing a titration, you have to choose an indicator that switches colors at the pH of the equivalence point.
Got it.
Because if you pick, let's say for example, an indicator that switches colors at pH 13, you're going to do this whole titration, and it's going to go, and it's going to stay, let's say that it goes from yellow to red. It's going to go yellow, 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 red. You'll be like, oh, I reached my equivalence point. No, you didn't. You passed it last year. It was over here. So you need an indicator that changes colors here. So you have to sort of predict before you put the indicator in when you're doing the titration. You have to know which one to put in. You need one that changes colors at pH 7 for this strong acid, and at pH 9-ish for this weak acid one. And in the strong acid, you've got a lot of room. You can pick one that changes at pH 4, pH 6, pH 8, pH 10, right? Because, you know, that's the pHs that are present during this large jump. With a weak acid, you have a small jump. You've got to get one that changes at like pH 8 or 9 or 10. So you don't have quite as much room for choice with a weak acid titration. Here's mathematically how you would choose if you are just wondering, you know, which one do I choose? The pH that you want it to change at which you want it to change, is going to be the pKa minus 1. So, for example, bromethymol blue, which I said we're going to come back to, it changes from yellow when it's acidic, it changes to blue when it's more basic. At what pH? Well, the Ka of bromethymol blue is going to be in a chart. You look it up, you find out that it's 1e to the negative 7. You squeaking, little child? You squeaking, my baby? The Ka is 1e to the negative 7. So what's the pKa?
6. 7.
7. At what pH is the color going to change from yellow to blue for bromethymol blue? 7 minus 1, which is 6. So it changes from yellow to blue at pH 6. So that's how you would choose that. Is you kind of go, well, I want it to change at something like pH 6, so I need to look for 1 times 10 to the negative 7th in my chart.
Got it.
So that's what you do. And now we are going to do a long problem. Here is the long problem.
Oh boy.
Yeah, I know. So take a look at this, and I'm going to do maybe part A and part B, and I'm going to ask you guys to pause and maybe do part C I'm not sure. I'll let you know. But here we go. So switching over to my black pen screen. Get your calculators and brains ready. Here we go. All right, here we go. Consider the titration of 40 milliliters of 0.2 molar perchloric acid by 0.1 molar potassium hydroxide. Calculate the pH of the resulting solution after the following volumes of potassium hydroxide have been added. A, nothing. All right, so let's do A. In part A, we have a squeaky baby. And in part A, what you're doing is you are dripping potassium hydroxide into perchloric acid. Perchloric acid is a strong acid, so that is KOH plus K, nope, HClO4, and that yields KClO4. That's your salt and your water. So that's your neutralization reaction. Because both of these are strong, because at least one of them is strong and both of them are, it's going to go all the way to the right. So this is a completed reaction. It's not going to sit in equilibrium, which it would if this was a weak acid and a weak base. But because one of them is strong, what we're dealing with is all the way to the right. And what we have is an amount of acid that is known, right? Yes. So what we have is 40.0 milliliters of perchloric acid solution. And this is that solutions thing that we learned of stoichiometry, which is to do a, what is this? An equality with milliliters and moles. This is the solutions equality, milliliters and moles. That's 1,000 milliliters of solution, milliliters of solution, so these cancel. And how many moles of HClO4 are there in 1,000 mils of solution? That's 0.2 moles. So 40 milliliters of solution is what you have, and the concentration of that solution goes in your equality here, because there are 0.2 moles per 1,000 mils. That is going to tell you, canceling the milliliters, how many moles of perchloric acid you started with, which is important. And what that is 40 times 0.2 divided by 1,000. That's 0.008 moles of perchloric acid. Okay? For A, you haven't added any base yet. So you need to find out the pH. How do you find out the pH?
You find out the
pH equals, what's the little formula for pH? Do you remember him?
No.
Negative log of what?
P of Ka.
Nope, of your H concentration.
H concentration.
This is your little formula for finding pH. What is our H plus concentration?
It's our acid concentration, which is 0.003 or whatever.
That's an 8, yeah.
Okay.
So it's the same as our acid concentration because this is a strong acid. A strong acid dissociates all of those H pluses. A weak acid would not do that. So when you have a weak acid, you can't just take the negative log of the weak acid's concentration. You have to,
it hasn't dissociated completely.
because it hasn't dissociated completely. But a strong acid, it has. So for a strong acid, you can go, oh, my acid concentration is 0.008. My H plus concentration is 0.008. So you do negative log of 0.008. And that gives you, I have this written down, oops, nope, sorry. That's moles. This is not concentration. It's moles per liter. They gave that to us already. It's negative log of 0.2. Because it has to be molar. We need this later, not yet. This is A. For the future. We need, sorry. Negative log of 0.2 molar, because it's the negative log of the H plus concentration, not the number of moles. So negative log of 0.2 is 0.699. That is the pH. Now, here's the thing. Your sig figs in this are a pain.
Okay.
Here is the rule. the pH decimals. How many decimals do I want in my pH? The number of pH decimals is equal to the number of sig figs in your concentration.
Okay.
Our concentration, when it is given to us, has 3 sig figs. That is the number of decimals that we should have in our pH.
Okay.
That is 1 decimal place, 2 decimal places, 3 decimal places. So that's going to come up, and it's important because it's screwy. So pH decimals, concentration sig figs. And I say that over and over in my head. pH decimals, concentration sig figs. So you've got to have that. It's a thing. All right, B. This is our initial pH before we have added any base.
Okay.
When we start adding base, what is going to happen to the pH?
It is going to go up.
It is going to go up. So let us watch it go up. All right, in B, we are going to take you're going to take this acid and you're going to add some base. And it is going to make water and salt. Yeah, see, this doesn't happen in part A. Because in part A you haven't added any base. In part B you have added base. There we go. Whew. In part B you have added base. And you start off with this number of moles of perchloric acid. So that's 0.008 moles of perchloric acid. Your next question is, how many moles of potassium hydroxide are there? Well, we've got to do a little bit of math here. And that's going to be how we did this thing. So that's going to be 10 milliliters, because in part B it's asking what's the pH after you've added 10 milliliters of base. Okay, so 10 milliliters of base of KOH solution. That's what you have. That's what you start with. You multiply it by your solutions equality, which is milliliters of KOH solution. There's 1,000 milliliters of KOH solution, and that's some number of moles of KOH, and it depends what is the concentration. It tells us up here somewhere, here, 0.1 molar KOH. Okay, 0.100, that's going to be important with our sig figs. So 0.100 moles of KOH are in 1,000 milliliters of KOH solution. And so that's going to be 10 times 0.1, which is, by the way, 1 divided by 1,000 is 1,000th, which is 0.001 moles of KOH. So this is 0.001 moles. And when you're doing this part, the stoichiometry part, the neutralization part, you need to be doing your stuff in moles. When we did our equilibrium stuff, we were doing that in molar, which is in concentration.
Okay.
So this is the stoichiometry portion of the math. It's got to be done in moles.
Okay.
Be aware of that. So before this reaction, you had 0.008 moles of perchloric acid and 0.001 moles of potassium hydroxide. You did not have any water yet, and you did not have any potassium chlorate yet. After this reaction happened, which one are you going to run out of first? This is actually a limiting reactant problem.
The KOH.
You're going to run out of the KOH. All of this will be used up, so there will not be any at the end. How much of this will be used up?
0.008 minus 0.001.
0.008 minus 0.001. So how much will be left after you are done?
0.007.
Yeah. How much of this will have been made?
0.001.
Yep, 0.001 moles of this will have been made, and 0.001 moles of this will have been made. Okay, so before, this is a chart that you need to set up because it's going to save you a lot of time with the stoichiometry. That's my husband, he's home. So it's a before and after chart. Okay,
We're going to see this a lot.
we're going to see this a lot. This is going to come up very frequently. You make a before and after chart. You put the number of moles in it. In your before and after chart, moles go in it. And there's none of these and there's some of these, and honestly water you kind of don't need to fill in because there's so much water that it's not changing.
Got it.
Essentially. So you can always just kind of strike out the water.
Okay.
So before you've got 0.008, after you've got 0.007, and you've got some salt here, which doesn't end up mattering because this salt does not affect the pH. Right?
Okay.
There's no acid, there's no base. So the thing that's affecting the pH is this guy,
Concentration of acid.
which is the concentration of acid. Now, here's the thing.
It's the moles of acid right now.
We now know the moles of acid. What is the concentration of acid? Well, your formula for concentration is molarity equals the number of moles over liters. The molarity equals, we know how many moles there are. There's 0.007 moles of acid. How many liters do we have? How many milliliters do we have? Well, we started off with 40 milliliters of acid, and we just dripped in 10 milliliters of base.
So we have 50 milliliters of solution.
So we have 50 milliliters of solution. That's really important to notice because this changes. When you're dripping something in, the liters change every single time. It changes. So yeah, you got to pay attention to that. So that's 0.05 liters or 50 mils, bump. So that's 0.007 divided by 0.05. And that gives you a concentration of 0.14 molar acid. And we're not quite done yet because it wants to know the pH. How do you calculate the pH?
pH equals the negative log of the concentration of my acid.
The negative log of my H plus. Yeah, now you remember. And so my pH is negative log of 0.14, which, if we're going to think about this, I would like to say that's almost the same as negative log of 0.1,
Okay.
which you can do in your head.
10 to the negative 1.
Yeah, so this is approximately
E to the negative 1.
1e to the negative 1, which is 1. So it's going to be approximately pH 1.
Which makes sense because you dripped in acid and so now it's less acidic than it was before.
Less acidic than it was before. So is it going to be above 1 or less, or is it going to be like 1 point something or 0.8 something? Is it more acidic than this or less acidic than this?
Then what?
Then 0.1. What's my pH going to be like? Is it going to be 1.1 or 0.9?
I don't know.
Well, we have a concentration of 0.14.
Sorry, I'm paying more attention.
Yeah, you're paying more attention to the baby. Well, let's see how it goes. That is more H pluses, so it's going to be more acidic than this,
Aha, okay.
right? So it's not going to be 1.1, it's going to be more like 0.9.
Okay.
You stick this in your calculator and you get 0.854. Okay?
Okay.
And that's B. Now, you have all of the skills necessary to do part C.
Okay.
You have all of the skills necessary to do part D, but it gets a little bit interesting. So I will come back and do part D. Yeah, so here we go. C. You go do part C. The answer is 1.301. See if you get it. D. All right, in D, you have added 80 milliliters. And so you end up with HClO4 plus KOH yields water and KClO4. You've got to do a before and after chart. Now, here's a little thing, which is when I do a before and after chart, I write before like this. Before. B4.
Okay.
And then after, I make a personal little joke to myself. This is after. So don't be confused when I do that, because I do that. All right. Nobody else does that. I'm the only one that does that. All right. Before and after. I know. I'm fabulous. All right. You're still starting with 0.008 moles. and you're starting with 80 milliliters of KOH. So that's 80 milliliters of KOH. Milliliters of KOH. 0.1, and so that's 0.008 moles. How about that? Look at that. Isn't that gorgeous? Yeah.
Uh-oh.
Yeah. So how much of it gets used up?
All of it.
All of both of them.
Well, that's interesting.
Yeah, what do you do?
Yeah, well, things multiplied by 0 is 0. That makes math easier.
Right, so what, is the pH 0?
Probably not, because that would be too easy.
Yeah, what is the pH when you have used up all of your acid and all of your base?
Probably 7. It should be neutral.
It's 7. When your acid and base are gone, your pH is driven by this.
Ooh.
This equilibrium is always present and in the background. And so if your strong acid and base give up and are no longer there, this is what is driving the pH now.
Ooh.
And so what you've got to do is go and say, okay, well, is water. This is 1 e to the negative 14 equals H plus times OH minus.
Concentration.
And they're equal.
Okay.
So 1 e to the negative 14 equals x squared,
Ooh.
right? So you take the square root. So x equals, and here's another bit of logarithm stuff in your head. The square root of a logarithm, when it's even here,
Okay.
you divide by 2.
Aha.
1 e to the negative 7. Because if you remember, 1 e to the negative 7 times 1 e to the negative 7, when you multiply them, you add.
You add.
So adding these two, you get the 14. So anyway, doing a square root of a logarithm that's even is easy. As long as this is a square rootable, because what is the square root of 1? It's 1.
Got it.
Okay? So you could do, for example, 4e to the negative 8. You can square root that and get 2e to the negative 4. You cannot do this one. It doesn't really work. You can do this one. Right?
Right.
And you can even do this one, 2.5 e to the negative 3. Because you can fiddle with it and force it to be 25 e to the negative, which way did I go? That's 4.
Okay.
And so that's square rooted 5e to the negative 2. Yeah, okay. So that's important to know because you are going to be expected to square root logarithm things in your head.
Oh boy.
Isn't that fun? Yeah. Yeah, the AP exam people are like, oh, they know how to do that. They can do that in their head. Anyway, so D, water. X is equal to 1 e negative 7. That is your concentration of H pluses. So what is your pH?
7.
Yeah, so your pH is negative log of, the baby is crying, of 1 e to the negative 7, which is 7. Okay? Whew. So D was sort of rough. Now let's do E.
Is E rough?
E is backwards. Because look at what happens with E. You end up with HClO4 and KOH. Yields H2O and KClO4. You okay, squeaky baby? Before and after. That's still 0.008 moles. When you do the math, this one is 0.01 moles. I'll leave that as an exercise for the reader. Water doesn't matter, 0. After this one is used up, there's none of that left because now there's more base.
Aha.
And so now you have 0.002 moles of base left over and 0.008 moles of salt. And so you want to do your pH and do, you know, negative log of your H concentration. But what is my concentration of H?
0. So
But what I do have is my concentration of OH. And so if you remember your square, I'm almost done, kiddo. It's fine. You're gonna make it. Hang on. We have to handle the baby. All right, we handled that baby. Now,
sure did.
more math. We don't have a relevant H plus concentration, but what we do have is an OH minus concentration. And if you remember the square, you can get to pH from pH to POH because added together they equal 14. H plus to OH minus, if you remember, because this is in aqueous solution, H plus times OH minus equals 1e to the negative 14. And so we can figure out the H plus concentration that is a result of the combination of this and this, because this is always going on in the background. So all these extra OHs are driving this left and eating up the majority of the H pluses that are coming from this. Okay.
Yes. Okay.
But there is a tiny, tiny amount of H plus still remaining, even though the concentration of hydroxide is relatively high. So what else do we have? We have this, which we can do the negative log of your OH minus concentration, can get you to the POH. So what I'm going to recommend is that we go from OH to POH to pH. We could go from OH to H plus to pH and divide 1e negative 14 by 0.002 and then do negative log this way. Doesn't matter, you could go either way. I'm going to go this way. So that's negative log of my OH minus concentration. That's my POH. So my POH is, I have this written down. Hey, I got to do the concentration.
Yeah.
This is in moles. So the concentration is 0.002 moles divided by my liters, which, how many mils was this? This is, yeah, E is 100 milliliters plus 100, go this way and then go this way some. E. So we started off with 40 milliliters, and in E we added 100. So going back down, that's, where'd it go? 0.002 moles divided by 0.14 liters. That gives you 0.0143 molar hydroxide. So that's negative log of 0.0143, and that gives you 1.845. That's your POH. That's really very basic.
Okay.
Okay. To get to pH, that's 14 minus 1.845. And that gives you 12.155. So that's pretty basic. And even with just a small hydroxide concentration like 0.002, it's relatively a high pH there. And that's because what you're dealing with is a strong base.
Aha.
And again, 3 pH decimals, because our concentration sig fig. And see, this is where it matters, is because this, it looks like it's 1, 2, 3, 4, 5. That's too many sig figs. pH decimals are equal to the concentration sig figs, not the pH sig figs, the pH decimal sig figs.
Ooh.
Yeah. So, and what's exciting is that WebAssign is often 1 off.
Oh. Good luck with that, guys.
I know. Yeah, it's exciting. Anyway, that's it. Ta-da. Bye.